Hello and welcome to the Unit 8 Section 2 video on sectors of circles. So we're going to talk about central angles and what those are to start off. A central angle is an angle whose vertex is the center of a circle. An arc is an unbroken part of the circle consisting of 2 points called endpoints and all the points on the circle between them. So here you kind of have a look at the different types of arcs that we have. A minor arc is an arc whose points are on or in the interior of a central angle. So here we have a central angle ABC, and the minor arc is the one that's on the inside of that angle. And we can use 2 letters to name that arc. We have arc AC, and we just use the endpoints of that arc to name the arc. Now a major arc is an arc whose points are on or in the exterior of the central angle. So the measure of a major arc is equal to 360 degrees minus the measure of the central angle. Okay, so here we have arc ADC. You have to use 3 letters to name this arc, because if we just named it arc AC, then the assumption would be that we're talking about this inside arc. So you have to use at least 3 letters to name a major arc. Now, if the endpoints of an arc lie on a diameter, the arc is a semicircle, and the measure of a semicircle is equal to 180 degrees. So again, we have to use 3 letters so we know which side we are talking about, because if we used EG only, we can be talking about this side of the circle or this side of the circle. We don't know which side. So minor arcs, you can use 2 letters. Major arcs and semicircles, you must use 3 letters to name the arc. A minor arc measure is the same as the central angle. The measure of a major arc is 360 minus that inside angle, and a semicircle is 180 degrees. So let's do an example of this. The circle graph shows the types of music sold during 1 week at a music store. We're going to find what the measure of BC is, so we are going to find this arc length. Well, to do that, we know that the measure of arc BC is going to be equal to the measure of angle BMC, that central angle that goes with it. Well, the measure of angle BMC is going to be 13% of 360, the whole, okay? Well, 13% as a decimal is 0.13. Multiply that by 360 degrees, and you're going to find that the measure of arc BC is 46.8 degrees. All right, now let's talk about the arc addition postulate. So if you remember back in Unit 1, we had segment addition and we also had angle addition. Now we're adding another type of addition, and that is the arc addition postulate. Adjacent arcs are arcs of the same circle that intersect at exactly 1 point. So here, RS and ST are adjacent arcs. So if we were to add up RS and ST, we would get the length of arc, or the measure of arc RT. And that's what we have here. The measure of an arc formed by 2 adjacent arcs is the sum of the measures of the 2 arcs. So the measure of arc ABC is equal to the measure of arc AB plus the measure of arc BC. You just take the 2 neighboring arcs and add them together to get the whole thing. So within a circle or congruent circles, congruent arcs are 2 arcs that have the same measure. In the figure, ST and UV have the same arc measure because the central angles are the same. You can use things that we already know from Unit 3 to make the determination that arcs are the same, and that's what we're going to show you here in example 2. Here we want to find the measure of CDE. So CDE is right here. Well, we know that the measure of arc CD is 90 degrees because the central angle that goes with it is 90 degrees. Now the measure of arc DE, which is the other piece that we need, well, we know that's going to be equal to the measure of DFE, the measure of angle DFE. Well, what is the measure of DFE? Well, it is 18 degrees because vertical angles are congruent. So that gives us 18 degrees here. So arcs that are made up from vertical angles are going to be congruent. And so now we can find that the measure of arc CDE is going to be the measure of arc CD plus the measure of arc DE. The measure of arc CD is 90 degrees. Measure of arc DE is 18 degrees. So the measure of arc CDE is going to be 108 degrees. All right, let's talk about radius and chords. If a circle, in a circle, if the radius or diameter is perpendicular to a chord, then it bisects the chord and its arc. So here we have a radius, and it's perpendicular to this chord. So the radius is going to bisect the chord, and it's going to bisect arc EF here. In a circle, the perpendicular bisector of a chord is a radius or diameter. So if you have a chord and you have a perpendicular bisector, you're going to do that with the radius or the diameter. So let's do a couple of examples with this. So in example 3, we're going to find what BD is. What's the length of BD? First, we're going to draw the radius AD, okay? Because we have radius AE, but if we connect A to D, this is also going to be a radius. So we know what the length of AD is. The length of AD is going to be 5 because AE is 3 plus 2 with segment addition, so that gives us 5 here. Then we're going to use the Pythagorean theorem to find what CD is because this is a right triangle. So we have CD squared plus AC squared is equal to AD squared. So CD is what we're looking for. So CD squared plus 3 squared equals 5 squared. So CD squared is going to be 16 because 25 minus 9 gives us 16. So CD is going to be 4. And it's only going to be positive 4 because we can't have negative length. In this case, CD is a length. So it has to be the positive length. And now we're going to find BD. So we know that BD is going to be twice the length of CD because it's bisected. So BD is going to be 8. The area of a sector is a fraction of the circle containing the sector. To find the area of a sector whose central angle measures m, we're going to multiply the area of a circle by m over 360. Now, what is the area of a circle? We will be talking about this more in the next unit, but the area of a circle is pi r squared. So we're going to take the area of the entire circle and multiply it by the angle measure divided by 360 because that gives us the fraction of the circle that we're interested in, okay? So let's show you how it works here with example 4. We want to find the area of sector MPN, and we're going to give our answer in terms of pi and rounded to the nearest hundredth. So the area, as stated up here, is going to be pi r squared times m over 360. So we have pi. Our radius is 3 inches, so we have 3. And our central angle is 80. So that's 80 over 360. So to find our answer in terms of pi, you're going to take everything that's not pi and do that math. So when you do 3 times 80, you get 3, well, first of all, 3 squared, that's 9. 9 times 80 divided by 360, that's going to give you 2. And then you have pi. Leave pi out of it to get your answer in terms of pi. And then we put our units, inches squared. And then you're going to use your calculator to approximate the answer to the nearest hundredth. So we get 6.28 inches squared. And here, do use your pi button on your calculator. Do not use just 3.14 because that will give you a rounding error. Use the pi button. For example 5, we want to find the sector area of EFG, this area. And we're going to give our answer in terms of pi once again, as well as rounded to nearest hundredth. So area again, pi r squared times m over 360. In this example, our radius is 6, and our m is 120. So the area, when we do all the numbers, we get 12 pi centimeters squared, and that is going to be approximately, when you put it in your calculator, 37.70 centimeters squared. Now, I do want to take a quick moment to tell you how to find the area of a segment. We aren't going to be focused so much on doing this specifically, but I do want to show you how it works. So the segment of a circle is a region bounded by an arc and its chord. So the shaded region here in the figure, to the right here, this is a segment of a circle, okay? To find the segment, the area of a segment, we're going to take the sector area and you're going to subtract the area of a triangle. So you know how to find the area of a triangle. You'll use your radius here and here, and you'll have the length of the chord, and you're going to find the area of that triangle. Subtract that from the area of the entire sector, and that will leave you with just the segment of the circle. So again, we're not going to do any specific examples of this. I just wanted to show you how it works. Now let's talk about arc length. In the same way that the area of a sector is a fraction of the area of a circle, the length of an arc is a fraction of the circumference of a circle. So the circumference, remember, is like the perimeter of a circle. It's the length of the entire outer edge of the circle. And the circumference of an entire circle is 2 pi r. It's just like with the segment, or the area, the sector area, we have to multiply the entire thing by the part that we're interested in. So again, we're going to be using m over 360. So let's do an example of this. In example 6, we want to find CD. We want to find this arc length. And we're going to give our answer in terms of pi and rounded. So we have L equals 2 pi r times m over 360. So again, we need our radius. So our radius here is going to be 10. And our angle is going to be 90. So we have 90 over 360. And so you do all the number parts, and that leaves you with 5 pi, and this is going to be in units of feet. This is just a length, so no square on the units. And that, when you put pi in your calculator, that's going to give you an approximate answer of 15.71 feet. In example 7, here we're just given the information. The length of the arc is 35 degrees, the radius is 3. So we're just going to put that information into our formula once again, 2 pi r times m over 360. So here our radius is 3. Our arc measure is 35. Put that over 360. Do all the numbers first, and that's going to give us 7/12. So we have 7 pi over 12, and the units here inches. And that's approximately, when you put in your calculator, 1.83 inches. So not necessarily terribly difficult. A lot of this is just use the formula, put in your information, get your answer out. All right, so that does it for this section talking about sectors of circles. Now in the next section, we are going to take a look at angles in sectors.